Everybody, this is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. Today's screencast is called the Not So Perfect Square, and we're going to continue to develop procedures for completing the square. If you haven't seen the screencast, Building the Perfect Square, you're going to want to view that one before this video. That previous video lays the groundwork for the work that we'll be doing in this screencast. In Unit 4, Topic 2, the students learn to model quadratic relationships with expressions by exploring patterns and connecting to area. Quadratics can be modeled using area diagrams of rectangles and squares. The algorithm for completing the square can be understood and derived from such diagrams. Completing the square is an emphasized concept in the Common Core State Standards, appearing at least 3 times. In reasoning with equations, we see that students need to use the method of completing the square to transform any quadratic equation in X into an equation of the form the square of the quantity X minus P equals Q that has the same solutions of the original quadratic. They also need to derive the quadratic formula from this form, and we're going to do that at the end of the screencast. Students are specifically expected to solve quadratic equations by completing the square. And when we think about interpreting functions, students are supposed to use the process of completing the square to show zeros, extreme values, and symmetry of a graph. It's not the other way around. Often, when we're pressed for time, we may look at students and say, well, just graph it on the graphing calculator, look at the vertex, there's your vertex form, you've completed the square. But that doesn't actually meet the standard as it's written out. The standard is very specific. Students are supposed to complete the square to reveal the features of the graph, not the other way around. Some of the helpful skills that students have learned. Algebraic expressions can be used as models of patterns. This is done in IM or Math 8, and it's also done earlier in Algebra 1. As I said before, this video is about building the not-so-perfect square. But when looking at students, we wouldn't want to tell them that we're building imperfect squares. In fact, we want them to think that they can build a perfect square for the trinomials that they'll see. So we would start by saying, build a perfect square from x squared plus 6x plus 7. Leave the two sides of the x squared tile open, and describe how the x tiles and unit tiles are arranged. Some students may complete a rectangle. This is a really important skill, and they should be applauded for their efforts, but we really want them to work on squares, not rectangles today. So while this is important for laying the groundwork of factoring and the distributive property when applied to quadratics, we really want to focus on that square. So if they do this, just remind them that this is important, but we want the square. We're going to start building our square the way we normally would, with our x squared tile and expanding it out. At this point, we're going to run into a problem, and this is what we want the students to say to us. We want the students to say, the task cannot be done. And we want them to say it cannot be done because there's no way to arrange this in the form of a perfect square. We always end up with some pieces missing. So then we want to ask students, well, if you could complete this, what would the dimensions be? And we want those students to then say, well, the dimensions of this should be x plus 3 squared, because it should be that both sides of this square have a length of 1 x tile and 3 unit tiles. Obviously, that's not the case, and students are going to say, but we're missing 2 unit tiles. And the moment that students say that we're missing 2 unit tiles, they're ready to see the equation. They're ready to see that the square of x plus 6x plus 7 is equal to the square of the quantity x plus 3 minus 2, or in other words, what should be the square of x plus 3, but missing 2 of the unit tiles. Students may connect completing the square to the vertex form of a quadratic function. This is one of many connections we hope students will make. When we complete the square, we are revealing key information about the parabola. The standard form gives us the vertical dilation and the y-intercept, but completing the square reveals all of the transformations and the location of the vertex. Let's take a look at another example. If we were in class looking at students, it would now be okay to say to them, this one's not going to be a perfect square. But we'd still say try to build the perfect square as best as you can for x squared plus 8x plus 19. We'd start the same way with our square tile and extend it out. Students may notice that they have 3 more unit tiles than they're supposed to have. And we'd ask them similar questions. So with the exception of those 3 tiles, what should this square be? What should those side lengths be? And they may notice that the side lengths should be a length of 1 x tile and 4 unit tiles, or x plus 4. But they have these 3 extras with which we don't know what to do. Now, some students may already guess what the equation should be. After all, in the previous diagram, we were missing 2 tiles, and so we had a subtraction of 2. But in this diagram, we have an extra 3 tiles. We may want to even ask students, what do they think the expression should be? In this case, it'll be the square of x plus 8x plus 19 equal to the square of the quantity x plus 4 and 3 extra or plus 3 unit tiles. Students may be able to connect the representations to the equation, but we now want them to be able to do this without using the tiles. After all, if we give them something with, say, 100 tiles in there, we don't want them to have to pull out 100 tiles just to do the problem. So we want to be able to do this in any scenario. So we got to start with what they know. They know that for a lead coefficient of 1, x squared plus bx plus c should equal the square of x plus h. And when that works out, we know that h is going to be exactly half of that middle term, that linear coefficient. And we know that c is going to be equal to the square of h. So let's try it out with an equation. So we're going to look at this expression, x squared plus 10x plus 36. Well, the first thing we'd want to know is what should be in our parentheses. Well, what should be in our parentheses is half of 10, 5. So we should be looking at the square of x plus 5. The problem is that when we do 5 squared, we don't get 36, we get 25. So the question is, do we have more tiles than we're supposed to have or less? We're supposed to have just 25 exactly, but we have 36, so we have more tiles. So how do we get from 25 to 36? And the answer is we add 11. And so our vertex form, or the completion of the square for this trinomial, is the square of the quantity x plus 5 plus 11. Let's go ahead and do another one. We're going to complete the square for the expression x squared plus 14x plus 45. We're going to go through the same process. We're supposed to have inside our parentheses half of 14, or 7. So we're supposed to be looking at the square of x plus 7. 7 squared is 49. But we don't want 49 because we're actually only looking at 45. So the question is the 45 more or less than what we're supposed to have? And clearly, it's less. So how do we get from 49 to 45? We subtract 4. And so the vertex form of this trinomial is the square of x plus 7 minus 4. Now we want to talk about building more not-so-perfect squares. All of the examples we've looked at so far have a lead coefficient of 1, but that's not the only kind of trinomial our students will see. So let's look at completing the square for the expression 3x squared plus 6x minus 3. All of these numbers are divisible by 3, which is intentional for the sake of the screencast. So we want to ask students, how many squares, and specifically x squareds, are we examining? The answer is 3. We're dealing with 3 of the x squared. So we're trying to look at building 3 squares simultaneously. So how can we write the expression for just one of those squares? Well, we can factor out the 3 so that we're looking at just x squared plus 2x minus 1. So what we're really saying is that we have 3 squares whose area is each described by x squared plus 3x minus 1. So now we want to put the vertex form in for each one of those individual squares. So we're going to go through the same process. Half of 2 is 1. 1 squared is positive 1. How do we get from positive 1 to negative 1? We subtract 2. So we're really looking at 3 squares that are supposed to be the square of x plus 1, but each of them is missing 2 unit pieces. And this is really critical because each square is missing 2 unit pieces, and we have 3 squares. What we really have is 3 squares of x plus 1, and we're missing 6 unit pieces in total. And there, we've just completed the square for a trinomial with a lead coefficient other than 1. But one of the key standards is to complete the square to derive the quadratic formula. So that's what we're going to do very briefly. We're going to start out with a typical trinomial, ax squared plus bx plus c equals 0. We're going to go through a slightly different path on this. 0 is divisible by any number other than 0, so we're just going to divide a from everything that we see. So we've divided a out of both sides of the equation. We've factored it out. We have x squared plus b over ax plus c over a. That c over a is kind of hard to deal with. We've got a lot of fractions going on. That can be visually difficult for even the best mathematician. So we're going to try and get rid of that c over a and just focus on what's on the left side. So we'll subtract it out from both sides. We now know that when we are completing the square, we need half of whatever the coefficient of the linear term is, or half of the b over a. So we literally need half of it, or b over 2a. But we're also going to subtract out that b over 2a squared, because when we square that x plus b over 2a, we're assuming we have all of those unit pieces there, and we don't. So we're going to subtract that out. But this is kind of messy, and really what we want to do is get as much over to the right side of the equation as possible. So that's what we'll do. We'll add that squared term to both sides of the equation. Well, now I have kind of a mess on the right side of the equation. So I want to simplify that. The first thing I want to do is square that fraction so that I can start to, combine like terms. So I now have b squared over 4a squared minus c over a on the right side. I want to group those into one expression, so I'm going to have to do something to combine like terms. So I'll get a common denominator. In doing so, I'm going to have b squared over 4a squared minus 4ac over 4a squared. I can now group those into one giant fraction. All I've done is combined like terms so that I have b squared minus 4ac all over 4a squared. I now have a perfect square on my left side of the equation, and I have this giant fraction on the right. But I can take the square root. So my equation now becomes x plus b over 2a equals plus or minus the square root of b squared minus 4ac over 4a squared. I can subtract the b over 2a from both sides, and I have my quadratic formula. Now, some people may look at this a little bit funny and say that's not the quadratic formula because they're used to negative b plus or minus the square root and then everything being represented over the denominator 2a. Both of these are valid forms of the quadratic equation. One of the advantages to viewing the quadratic equation this way is that it better parallels how students will perceive the mathematics when they go to solve a problem using completing the square. They're always going to end up with their axis of symmetry plus or minus a square root, and that square root always represents the distance to the left or to the right of your axis of symmetry. So there's some advantage to leaving the quadratic formula like this. It's your axis of symmetry plus or minus the distance that needs to be traveled on the coordinate plane to get to either of your x-intercepts. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.